Kirchoff's voltage law. This is probably the sort of basic thing that we will use over and over and over again. Kirchoff's voltage law states that the summation of voltage drops around any closed loop is equal to 0. And if you think about that, that should make intuitive sense. If I start at this point in the circuit and go all the way around and come back to that point in the circuit, I should still be at whatever potential I was at when I started with. It shouldn't have gone up or gone down while I was working my way around. So the summation of all of those voltage drops has got to be equal to 0. And we will make use of that over and over again. So that's Kirchoff's voltage law. Sometimes you'll just see us abbreviate that to KVL. Kirchoff's current law states that the summation of currents into and out of a node is equal to 0. A node being some point where wires come together in your circuit. And again, hopefully that should seem to make intuitive sense just from a conservation standpoint. We're not creating or destroying electrons, and so any that go in have to come out someplace else. And so we'll also make use of that, the summation of currents being equal to 0. All right, so with those two things, then we can start looking at more interesting circuits than just a single element. So let's look at combining resistances in parallel. Starting with, what does it mean to be in parallel? It has a very specific meaning. Exactly. For two things to be in parallel, the same voltage has to appear across both of those elements. And so that's the basic requirement for two devices to be considered in parallel. The same voltage is going to appear across them. And we'll make use of that in analyzing what's going on. So here's the sort of circuit equivalent and the hydraulic equivalent with a couple of resistors, or restrictors, excuse me, on this side. So how are we going to go about calculating what these, if I know V, how am I going to go about calculating what these I's are? And in particular, what I want to get at is, what's the equivalent resistance created by those two resistors that are in parallel? How are we going to do it? Yes?
Combine Ohm's law with Kirchoff's current law. Since they split the nodes in and out, so you can sum the currents there and there and then.
Well, okay, I can write this expression. So there's Kirchoff's current law being applied. The I total is I1 plus I2. Okay? So let's call this one R1 and this one R2. So we've got I1, whoops, I1 R1 equals V, and I2 R2 equals V, and oh, okay, all right, so you're gonna, yeah, let's do it that, we can do it that way. I1 equals V over R1, I2 equals V over R2, and then, yep, going to use this so that we've got I total is V over R2 plus V over R1. Okay, so we'll skip the algebra steps. So in the two resistor case, the two resistant, the R equivalent that we would come up with is the product of the resistances over their sum, R1, R2 over R1, R1 plus R2. In the general case, if there are more than two resistances, 1 over the total is equal to 1 over R1 plus 1 over R2 plus 1 over R3, dot, dot, dot. Oh, you know, look at that. And then R1 plus the product over the sums. Okay. Hopefully fairly straightforward. Okay, resistances in series. So once again, what does it mean to be, for two things to be in series? Yep, same current. Whoops. Same current has to be flowing through both devices for them to be considered in series. So how do we go about figuring out what the equivalent resistance, that's where we're at for both of these, is what's the equivalent resistance of two resistors in series? Pardon? Use KVL, okay. So how would I use KVL? We're going to start with V. Okay. So what? Okay. So all right. So now here's the question. So we got IR1. So what symbol am I putting between the V and the IR1? Minus. Yes. I start with this much voltage and then I drop voltages across the resistors. So V minus IR1 minus I, the same I, R2 is equal to 0. So we can flop things around here. V equals I R1 plus I R2, I times R1 plus R2. So resistors in series add simply algebraically. Now, this is always seems to be, so people want to do this a lot. So they calculate I need a 1.05 kilo ohm resistor or a 1.05 mega ohm resistor. Let's do it that way, okay? And so they say, oh, I'm going to put a 1 mega ohm resistor in series with, what would that be, a 5 kilo ohm resistor. Does that make sense? Yes? No? I see lots of heads shaking up and down. I'll give you a hint. No. Exactly. You can put those two resistors in series, and you won't know significantly more about what that total resistance is than if you only had one of them. Because the tolerance on the mega ohm resistor is going to swamp the value of this little resistor that you're adding on. Okay, so this is a classic thing that students do early on. They've calculated what this value is, and so they want to put a chain of resistors together, all standard sized resistors, to get to this exact value that they've calculated. They ignore the fact that the uncertainty in the large resistor completely swamps any knowledge or any value of the smaller resistor that you've added. So please don't do that. Look at the tolerance. If you calculate 105 as a value, and then go with the standard value of 1, because that's 105 is still within the tolerances of it. Yes. If you're trying to get a minimum resistance, if you'd rather have the resistance be over than under, then why wouldn't you just go to the next larger size standard resistor? So I mean that's the I'm sort of harping on this because it's a really common thing that I see. People assign a greater degree of accuracy to the physical components than they actually exhibit. And so you've calculated this thing on paper and you want to try and make it like what you calculated on paper, and that really ignores the reality of the tolerances on these physical devices. All right, so, okay, writing loop equations. All right, so we've, Kirchoff's voltage law, we can apply over and over again, and when we do that within a circuit, we talk about writing loop equations. So we've already been through it, so we would just make a loop around through the circuit and add up all of the voltage sources and voltage drops associated with components. The key to making this work is to choose a set of directions for the current flow and be consistent about it. And my first circuit course books said that there's nothing magic about it, but there's some certain beauty to using clockwise current flows. So it doesn't matter, clockwise, counterclockwise, but pick one and stick with it. So we've got I1 and I2. And then yes. Yes, a loop is a path that you can take that will start at one spot and get you back to that same spot. And generally, we're going to try and make as tight a loop as possible, because there's also a loop that I could draw out here, but that would actually incorporate the loop that was running here. And we don't need multiples of them. We only want to make sure that there's only one possible or one loop that's represented. So we could write the equation for this. We start with V and we go minus I1 times R1, and then minus I1 times R3. And here's one of the other things that you have to be careful of when you're writing loop equations. You've got to capture all of the currents that are going through every component, not just the reaction to the current loop that you are that you are analyzing right now. So we're looking at the loop for I1, but R3 has not only the current loop from our I1 running through it, it also has the current loop from I2, and it's flowing in the opposite direction. So you need to be sure and capture that sign change, I2 times R3. That represents the current flowing, or the voltage drop across R3 due both to I1 and to I2. And then we're back to I1 times R4. Whoops, R4. That whole shooting match is equal to 0. And then for I2, there's just two parts. There's no voltage source, so we've got minus I2 R3. And once again, we've got the other side of the loop that's rolling through R3. So we've got a plus I1 R3 minus I2 R2 is equal to 0. I think I got those signs right. So once you've gotten the loop equations, you can solve them any number of standard ways. We know the values of R and V. We've got two equations, two unknowns. MATLAB will do it quickly. You can do it algebraically if you'd like. The key, though, is getting those loop equations written in a way that has a consistent convention for the direction of the current flow and for components that are parts of multiple loops, that you capture the current flow from both of those loops every time you treat that component or make the element, the loop equation element, associated with that. What happens if I go through and I calculate that I2 is minus a half a milliamp? What has that told me? Pardon? Yeah, it's just if you end up calculating a minus value for the current, that just means that the direction of the arrow that you assumed was wrong. Current's actually flowing the other way. Perfectly valid result. All right, so some arrangements of components appear so often that we actually give them a special name. And so this arrangement of a voltage source and two resistors in series where we've taken a tap off at the center, you're going to see this over and over again. It's referred to as a voltage divider. And so what we're at is, how do we figure out what the voltage is going to be at V0? So V0 is going to be equal to, let's do this, which kind of gives it away. Okay, so that's what the voltage is going to be. How do I figure out what I1 is going to be? Yeah, we just apply KVL. So we've got V minus I1R1 minus I1R2 is equal to 0. If we know V and we know the values of R's, we can solve for the I. And with that I, we can calculate what that voltage is. We can actually, yeah, I got room. I should have room. Summarize that. VO, if we pull all these things together, VO is going to be equal to VI, the driving voltage, times R2 over R1 plus R2. R1 plus R2 because that's going to set the total amount of current that's flowing. VI, so VI over R1 plus R2 is equal to I. All right. Okay, so let's look at a realistic situation. You're going to have to measure what that resistance is. And we want to know, we know that the value of, we know that the measurement is actually going to result in some disturbance of the circuit. And we're going to figure out, we need to figure out how much disturbance would we expect to see. How would we go about doing that? So when I make this measurement, I'm going to put RM in parallel with R2. So what am I going to, so I've recognized that. What's it going to do? How is it going to change VO? It will change the equivalent R2, okay? So it's gonna change that, but how is it going to change the voltage? You can predict right now how it's going to change the voltage. I heard somebody say lower. Come on, own up to it. Okay, why? You're right. So be strong. The resistance is going to be less overall. Why? Exactly. Whenever you have two resistances in parallel, if you think back to the hydraulic analogy, adding another resistance adds another flow path. That's going to cause a lower voltage drop to appear across that because you've lowered the overall resistance to flow. The same is true. Whenever you put two resistors in parallel, the combined resistance will be less than the smaller of those two resistors that you put in parallel. So if I start out, let's my real example or physical, or put numbers to it. 10K. R1 equals R2 is equal to 10K, and Rm is equal to a mega ohm. And if Vi is, what did I use for Vi? 10 volts. Nice round numbers, make it easy to do. What voltage would I expect to measure? Something slightly less than 5 volts. Okay, we could go that just based on what we've said, but numerically, how much less? How would I figure it out? Let's just talk me through what I need to do. the equivalent resistance of R2 and RM in parallel. So I'll give that to you. That's 9.9K.
And then if you use the voltage divider law that we derived earlier,
Okay, so, and what's that?
it'll be 9.9K divided by 9.9K plus 10K. All that multiplied by 10 volts.
Okay. And that comes out to 4.975 volts. So with two equal valued resistors here, we would expect it to divide it exactly in half, 5 volts from a 10 volt supply. We got 4.975. Let me assure you, within the accuracy of the measurements and the tolerance of the parts you're going to have, that's as good as 5 volts. Okay, let's run this again. Say R1 equals R2 equals a mega ohm. Now what are we going to measure? Should be able to do this one in your head, really. Pardon? Yeah, 3.33 volts. Because if I've got a mega ohm for the value of R2 and I put it in parallel with a mega ohm of meter resistance, that's going to give me a half a mega ohm of equivalent resistance. So now this becomes a half over 1 plus a half or a third. And so if we're trying to make a measurement with an instrument whose resistance, whose internal resistance is the same as the elements that in our circuit, we're going to end up making gross distortions of what the situation is in the circuit just by adding that resistance measurement. That's why we try and tell you to keep the values of your resistors down in the tens to hundreds of kilo ohms range, not let them get up into the mega ohms. And the reason for it, sometimes you can't get around it. But what you have to recognize is if you can't get around it, you no longer have the ability to go in and probe that circuit and figure out what's going on with it. The act of probing it is going to make such a large disturbance that if you just took that measurement, you'd think you screwed everything up. When in point of fact, the actual process of doing the measurement is what caused the problem. In the back and then over here. What keeps you from using higher and higher resistances for your... Well, this resistance here is the internal resistance of the meter. So it's not something that, so the amount of current that is drawn by the measurement circuitry inside the device is equivalent to a mega ohm resistor. So you could go buy a better meter that had 10 or 100 mega ohms. And in fact, on oscilloscope probes, you can change between 1 times and 10 times because the actual current that's being measured inside the device is much less. And so you can actually flip in a series resistance to raise the resistance of the probe. But that lowers the voltage that gets measured inside. So you have to compensate for that.